My name is Simon Zelazny. I'm here from Grindr, as are some of my colleagues here. I want to show of hands, first of all, who has Elixir or Erlang code in production? Nice. All right. I said intermediate advanced, so I got what I wanted. Who's doing a production support for their code? Yeah. Who's on call right now? All right. Who has had to debug stuff live in production on a live node? Yeah, nice. Who has killed a node with eprof with 100,000 users? Yeah. All right. So who has had to sell technology to management? Okay. So this is pretty much where we're coming from. We tried to cover some ground, some technical, some non-technical, but our talk is called Cajoling the Bird, about how we squeezed more out of Phoenix PubSub because we had no other choice. So first of all, I'd like to say who is responsible for this work, because it's not me alone. It's our entire team, Rafal, Ben, Toby, and myself. You can check them out on GitHub. We work together, we pair program. This has been a joint effort from the start. Okay, so what is the app? Grindr, the app, is the best gay dating app on the market. I took that from the Oxford Dictionary. This is what it looks like. So you load up the app on your phone, and it shows you nearby guys, and you can chat with them and go on dates, pick and choose. And so there's a problem that we wanted to tackle, and that problem was stale presence indication in the app, which means that these guys would show up, but they wouldn't actually be there, or they were there, but they got off, and it was rather confusing for users. And the whole problem stemmed from the architecture which supported it. So we have these clients, and these clients would make a call to say, get my nearby guys, at the same time updating their location, and they would get their nearby guys. The problem with that, as you can see, is that it's just a simple polling architecture. So we only get the presence information is only as fresh as the poll interval. And so we get these faults such as ambiguity. I don't know if this person is actually online or not. We have the problem that it's not real time, so I can't really trust this indication. And our hypothesis is that we get lower engagement because people are not as invested into the connection. And so what we want is clarity, online, offline, I'm done, I know what this means. And real-time relevance, and therefore higher engagement. So we have XMPP, we have these geolocation APIs. So some solutions were explored how to get this working. So the most obvious solution is just update more frequently, right? And just spin up those machines, hundreds and hundreds of machines. And that was a solution that easily comes to mind, but was easily dismissed because of scaling issues. Leverage the big corporations' IoT offering. They do everything. They do presence, they do online, offline detection. But our SRE chief said there's no way we're getting locked into that. Then there was the XMPP option, which was let's solve everything with XMPP, and that was not successful in the past at Grindr, and we felt we shouldn't push that avenue of research any further because we pretty much ended up like this famous knight. And so we have Beam developers in the company, and the Beam developers asked if people have heard about the bird, and they did. And so we introduced this bird, the Phoenix framework. We said, look, this is something that pretty much fits our use case. It's open source. It has modern. I mean, I'm preaching to the crowd. Let's skip this. So it has presence built in, which is exactly our use case. The presence is implemented with CRDTs, which means you don't have amnesia transaction woes. There's leaderless replication, which feeds into the same. And we're already running on the Beam, so in a sense, the foot is in the door. We have proven the technology, so let's give it a shot. And so we did. So we said, okay, let's do this. We have 1 day. Let's knock this out. And we made a tiny, tiny project in Phoenix using Phoenix channels that contain a backend component and a front-end component. And we presented the results to the company, and it was this little tiny demo where one simulator logged in. That was user 1. Then the other user logged in. and we got the presence indication right away. And this was big because this was not happening in the app. As you can see, the right user is not subscribed to the left user, but this was just a technology demo. It worked, and we got buy-in. So we proceeded with actually implementing this and seeing how far we can take it. So we wrote the test, we wrote the use cases, we figured out the contract with the client, and let's try the simplest possible thing. So if you know Phoenix channels, we just everyone has their own presence channel. When I log in, that's my presence channel. People can subscribe to it. So if I went to subscribe to my nearest buddies, my 50 favorite friends, then I would make 50. I would make 50 channels. So this would look like this. So every topic, which is the presence indication, would be a separate channel opened from the client app. So this was the most straightforward thing to do. It worked, but as we all have to support stuff in production, we really wanted to make sure that it would support our production traffic. And so this is where the talk starts, because it obviously did not support it out of the box. So we can't just put things in production at Grindr because we have 10 million daily users. There's constant churn. We have up to 2,000 logins per second. There's 200,000 sessions online at any given time. So we can't really, and we want whatever service is coming online to be compatible with everything else. So we can't just say, oh, let's read this and these people won't be able to chat. So we wanted to deploy a service that can withstand production traffic. So we had to load test it. And if obviously you know that there's a thing with load testing tools, and every company seems to write their own load testing tool. So we did as well, because I think it's a thing. And so this is actually another iteration of our load testing tooling in general. We wanted to have a declarative format for the tests that we can easily specify. We can change numbers. Here we don't have parameterized steps, but these are steps that the clients would execute. And so we dreamed it, and we built it in Elixir. And the philosophy is easy. You just write a single scenario. You write the process that executes the single scenario, and then you run them in parallel. And that's why everyone writes their own load testing tool, because it's trivial. And once you have metrics on everything, and once the language to create the scenarios is flexible enough so that you can push and prod your system, then you have a great load testing tool. So if there's one thing you take away from this talk is please write your own load testing tool for your use case. It's a very small investment and a very big return on that investment. So here you can see our load test. It's literally tmux frames running an eScript on 10 different machines. So that's 90,000 users. It looks better when there's 9. We usually run 100 multiples of 10, but this looks more aesthetically pleasing. So this is pretty much what we did. We wrote the scenarios, we simulated the clients, and we hammered the system, and of course it fell over very quickly. The memory usage just went off the charts right away, so we didn't even get a couple of minutes of runtime out of the system. So what? We had to formulate a hypothesis. What's going on? How is this happening? And so the obvious thing is that there's a lot of processes being created. The clients open one channel per subscription. If we increase the subscription size, we're creating tons of channels, and that is probably not helping the memory usage. What more? Each channel does very little work and allocates very little memory, so it just kind of sleeps there and slowly accumulates memory. And in aggregate, that's a lot of memory. So what we did is we used a recon. We assessed what's going on, and in fact, there was hundreds of thousands of processes, each with some significant but not too large amount of memory, and they were just eating up the system, system's available resources. So what's the Erlang or Elixir solution to this? Can anyone tell me? Process is not doing any work, and it's accumulating memory. What do we need to do? Yes, exactly. So we said, okay, let's do this. Oh, yeah, a little side note. So Kent Beck says, call your shots. And I think that's a super good advice. So before you make any changes, model the system and say, okay, if I make this change, I predict that this and this will happen. And Rafael takes it a step further because he's a compulsive gambler, and he says, let's bet. And he says, I'll buy you lunch, or I'll buy you a beer, whatever. And so we call it bet-driven development. So we make bets, and we indeed hibernate the channels, and of course that works. So our memory usage is reasonable. It does kind of pollute the code with a different concern. So the longer term solution is not to hibernate stuff manually, but just to use Erl full sweep after. Trivia question, what units is Erl full sweep after expressed in? Does anyone know? I checked today in the Erlang manual. This is generational garbage collections allowed before triggering a full sweep garbage collection. The default is like 65,000. If you set it very low, you're just using up CPU, but the memory stays low. So this is what we did. That all worked. It was great. We cranked up the load, and the server side seemed fine, but since we had this wonderful load testing tool where we measured everything, we saw that the client response time, the client side response time, the server would say, oh, this is done, this is done, this is done. But the client side response time were like, you know, the tail latencies were very high. It was not very impressive. And so we started running around. What's wrong? This is broken. This is not going to work. The answer was very trivial. But someone mentioned Konrad Malawski's talk from Lambda Days in Krakow in Poland, the need for async. This is about Scala, but there's a very good piece in there about this, about the way we read data off sockets. So there's select and there's epoll. Select is, I guess, more lightweight on the system side. Epoll takes more to set up. The Erlang default, the default option is nothing. Just use the default select facility provided by the kernel. You have to say +k true. And then if you have lots of sockets with little traffic on each of the socket, you want to use epoll. If you have a few sockets and you're serving massive amounts of data, it doesn't matter because you don't have to pay the penalty. So yeah, so we called our shots again. There was beers involved, and the real world responded that the hypothesis was correct. So that's a trivial thing that you may sometimes forget. Or if you're developing large-scale systems, just always put +k and don't go back to it. It's evidently, in our case, it made a world of a difference. And so, fine, we solved this little problem, so we crank it up. It's very easy because we just change the number in the E script, and it hammers the system. It's very satisfying. And so, again, this time with much heavier load. I think it was 100,000 users, 100,000 sessions, somewhere around there. And our 64 gigs of RAM, which Grindr graciously allows us to load test on, it just went like that, and the system fell over again. And at this point, it was clear that this was not an explosion of RAM usage. It was just the use case that we were supporting consumed a lot of memory. And so how can we reduce our RAM footprint in general if it's a nice linearly scalable model? Any questions? With Phoenix, we have Phoenix channels. How do we remove RAM usage? By removing the Phoenix channels. And so what we did was we left the single channel that the client was connecting with, and we used Phoenix requests to sign this channel up internally to the PubSub topics. And therefore, instead of spawning 50 channels for a subscription of 50 people, we just spawned one and internally subscribed to those 50 people. That was great. We used Phoenix requests, wrote a tiny bit of code. Up till now, this was like 50 lines of code. We had to write a bit more to support these use cases. We called our shots. Everything went down. It was great. So we are on the way to production support, but this is not something we can throw in right away. So we put more load, yet more load, and then the fun stuff starts happening. So what we see is on the server side, we start getting gen server call timeouts in presence track. And if you've had gen server timeouts, you know that they're not fun. Because it means there's some kind of bottleneck in the system and things are timing out. We're waiting for the presence tracker. So at this point, it's not in our code. It's not in our VM options. We have to open up PubSub internals. And so the tracker architecture, who's aware, who has experience with the tracker architecture? Yeah. So how many tracker processes per node? Oh, it's up there. One. So there's one tracker process per node. And this tracker process does a lot of things because it handles actual presence registrations. It handles information coming in from other nodes in the cluster. And it handles GET requests, quote unquote, for getting the data from the process. And so that was clearly our bottleneck. So we had to get to, this is how it looks. So in theory, what we would present to our CTO is this channel is subscribed to this and that. But what's actually happening is that every client, if we want to get that guy, that guy, that guy, that guy, and that guy's status, we have to make all those calls to the tracker process. And this is one tracker process on the entire node. So as you can see here, 4 clients want to get a subscription list of 4, a presence list of 4 other clients, and the tracker is having to handle all of that. So this is, as the picture shows, this is clearly a bottleneck. So what's the solution to this? It's happening in Phoenix PubSub. Yeah. So yeah, that's the Elixir solution, is sharding or share nothing parallelism. And the interesting thing about this one is that while the PubSub server is, the PubSub shards are delineated by caller PID, the tracker shards cannot be, what do you call it? We cannot dispatch on the caller PID. So we have to dispatch on the topic. So we hash the topic, and as many tracker shards as we have, we dispatch the given requests to those trackers. And so this gives us, at scale, a slightly more appealing graph. I couldn't make graphists do this in a straight way. So that's, but we have 16 requests, and each tracker shard handles only 4 of them. And this allowed us to scale linearly, and it worked. But it was not easy to do, because who went to the macro talk in the morning? Yeah, so we broke the first commandment, which is don't use macros, but we had to, because there was a hard-coded reference to __ module in the Phoenix tracker, so we wrote this code. We're not using this code in production anymore, but for a while we were. So this is a builder that just builds a list of at pool size tracker modules. So we had 10, we experimented with various sizes. There's a pull request that unhackifies this. And so the request, the result is that it indeed did work. We removed that bottleneck. That presence tracker track call was no longer timing out. So we decided to really crank it up. Let's see if we can handle all of Grindr traffic on one node, just in case everything else goes down, that we don't actually lose our availability. And as added flavor, let's have everyone subscribe to 500 other people. And what happened was that indeed we did create the load, but on the server side, things looked strange. So the CPU is not maxing out, neither user nor system. The memory was okay, flat. The network was not saturated. We could still download images from Imager. It all worked. However, we couldn't do it. The publishing rates were slow. Things were slowing down on the receiver side. And so we had no idea where to look until our esteemed colleague had the idea that this was contention in the Erlang VM. And so how to find contention in the Erlang VM? So there's a tool called LCNT, and you have to enable it while compiling Erlang with -- enable LCNT. And the documentation says, this tool was mainly developed to help Erlang runtime developers iron out potential and generic bottlenecks. Ours was both potential and generic. We weren't runtime developers, but we used this tool to great effect. So what you do is you build this virtual machine, and when the log counter thingy is compiled in, when that option is compiled into the VM, then all operations on the VM that require a lock are accounted for. So it takes a toll. You can't really make it go as fast. So what you do is you run it at a reasonably low load. You tell it to start counting and keep track of what's happening, and then you get nice tables. So in our case, we found that there are many of these locks. And if you look in the C source code, you'll see explanations of all of them. There's a lot. I can't say I know anything about the 2 that I am going to speak about, which is pixlock and proclink. And those 2 are locks taken when a process is created in the system, which is an atomic operation, so there's no way to avoid it. And the proclink, which happens when a process is linked to. Run queue is when schedulers need to pop a process into their queue. So there's clearly contention there, so that's rather unavoidable. But the 22% wait time and 20% wait time on proclink was clearly very bad. Additionally, I'm not going to go into details, but this is like the aggregate table. There are tables with particular locks, and it was clear that there was one pix lock that was causing all the trouble. And so it means we were spawning too many processes. So when we looked into PubSub internals, again, we found that do broadcast does this for every broadcast message. It takes every PubSub shard, and it spawns a process to send that message, which is nice because all the messages go out at once. But if you have 8,000 messages per second and 128 shards, then you have 1 million processes spawned per second. I made up these numbers because it's 1 million. We were hitting 1 million around, and so that shows the limits of parallelism in the Erlang VM, because ultimately there are locks. Ultimately, it's running C code, and ultimately you have only as many schedulers as CPU cores. So we have to help the man behind the curtain that's trying to provide the illusion of parallelism. And the way to do that is to just loop over the shards. So before we had this code, you see the task being spawned here, linked and then unlinked. That's the proc link. Spawning the function is the pixlock. And then we await for them. We just did that. For shard, in pool size, we just do the broadcast. Do the messages arrive at different times? Yes, they do. But does this work at scale? Yes, it does. And so the lock contention was removed. As you can see, most of the time spent waiting for stuff in the VM was spent waiting to pick processes off the queue. So we effectively removed that bottleneck, and that pull request was reviewed and accepted a long time ago by the Phoenix team. So that's in there. Hopefully, or maybe not. We wish that you will see the effects of this as soon as possible in your production setup. So we had all this stuff going. We had 200,000 clients, but the tracker operations were still slow. It's the tracker again, right? So what's up? We need more data. So we started instrumenting things furiously. And there's no slide for this, but don't make too many histograms in Exometer, because they run on Gen server processes as well, and you may slow down your entire system because of the histograms. But we did put metrics on everything, on all interesting function calls. We ran the Erlang System Monitor, which is an interesting tool that tells you if something spends a lot of time in the scheduler, therefore blocking other processes from having a go at it. And so the monitor pointed to phoenix.tracker.state.merge, and that inside calls maps from list and maps to list. And now, maps from list and maps to list are no longer implemented in Erlang or Elixir because they are implemented in C. So they are built-in functions. And if you look at the Erlang manual, the original Erlang manual in the lists module, there's the ---- operator, which we had used once in production. It was bad. And it says, do not use this ---- set difference on lists because it does not bump productions. So what that means is the process that gets to execute this ---- list of 2,000 versus list of 4,000 actually sits there in the scheduler until all that C code goes through all the allocations, all the creating of the Erl struct, the NIF structs, and all that before it comes back out. So effectively, it removes parallelism from the system. And that's also what maps from list and to list do. They just grab it, and they run until they're done. So we figured, well, this is bad because we're hitting the implementation limits. There's a very cool presentation by Steve Vinosky about how to modify your system so that you don't hit these limits. It's very interesting. We read that. We kind of got into all this. We started making micro benchmarks, and we didn't know what to do. And so, luckily, at that time, Erlang and Elixir Factory San Francisco was going on. So we went, again, all of us. And there's a ton of very knowledgeable folks there, as here. And we grabbed Lucas Larson from the OTP team. And we said, we're having this problem with maps, and maps don't bump productions. And Lucas says, oh, but Erlang 20 has dirty BIFs. Just use dirty BIFs. So we said, great, let's use dirty BIFs. We went back to the source code. We coded up. We moved the maps from list and to list from the regular BIF to the dirty BIF. We made that run dirty scheduler. The Steve Vinosky presentation goes into depth about that. I can't. Anyway, we wrote the dirty BIFs. We called our shots. We said, yes, this is going to make a difference. This is going to unlock the VM. And yes, it did unlock the VM. And we ran the load tests, and it didn't help a single bit. We were still have. Yeah. So that was fun. It was very fun. It was an educational experience, but it did not help in the large scheme of things. So we just sat down and we thought about where the tracker spends its time. So these are the three crucial functions in the tracker. One is track. All of them are actually, well, the first two are called when a client logs in, because it tells the tracker to track its present state, and then it says, oh, for everyone I'm interested in, list me whether they are present in the app or not. And then there's handle info, which is every 1.5 seconds or however often you configure it, gets the information from all the other nodes about what's happening with presence. And again, this is no longer one process on the node. This is like 100 processes on the node. But still, all these are serialized operations. So if someone's calling track and you want to call list, that's not going to happen. It's going to go on the process queue, and you're going to wait for it. So we had been focusing on this handle diff, which does these huge operations on maps. We had forgotten to look at tracker list, which was being called much more often than handle diff. And so, very quickly, how much time do I have? Let's do this. So gen servers are there to hold state, right? So you have a process, and you want to maintain the state for the lifetime of the process. So the tracker state struct holds the state of a tracker process, and it has a lot of very interesting things related to bookkeeping in the CRDT cluster. But it also has this thing called values, and values is an ETS ID. So the actual values, the actual heavyweight data is not kept in the process memory, it's kept in an ETS table. But when you make a call to tracker list, what happens is we take the name of the tracker, we gen server call list, that gives us the ETS, and then the state module can talk to that ETS. And that's the list, it's filtered by dead replicas and whatnot. So this makes sure that that anything we get from the topic is nice and clean and has no logical errors. But it also is a gen server call. And it's also called 500 times when one person logs in, times 1,000 logins per second, or 2,000, because that's going to be 1 million again. It can be called many times. So what we figured was that we need to come up with a dirty solution. And you know, Mnesia does dirty solutions. There's a lot. Every clean solution has a co-solution that's dirty. And so we figured, let's use this. We have an ETS table. It is named. It's going to be as hacky as that. So we figured we'll just name the table, make the name public per tracker shard, and then go straight to the table. So what happens is we can access the data directly because the name is known. We bypass the gen server call completely. We will get stale results because that tracker list thing removes information from replicas that are down or that we have temporarily identified as down. But we don't care. That's something we can, if this is during a deployment, this will roll over very quickly. The upside is we have tracker dirty list, and we have blazing fast presence tracking. And so having done all that, this was about 2 months of work. We loaded up a ton of users, 4,000 logins per second, and we managed to get what we aimed for. On a Friday at 6 p.m., we did 12 million events per minute. You can see the satisfying tweaking of the load here. And we got it working. So that was our thing. There was 2 pull requests to Phoenix PubSub that came out of this. This failed dirty BIF implementation that came out of this. A lot of practical knowledge. A very good load testing tool that is now used throughout the company, not only for Erlang stuff. So we were very happy. And there were some takeaways. Do the naive thing first. We didn't try to scale this or optimize this from the outset. We said, hey, here's this minimal code. It works. You can build a demo, show it to the CEO. Wow, right? And then we have to do the work. But it did work, and it did prove that the technology supports it. Don't trust micro benchmarks unless you really know what you're doing. I guess we didn't. So we were very happy with the micro benchmarks, but that wasn't what was happening at scale. And instrument your code. So when you load test, you can see the exact effects of what's going on. It's especially important to have histograms of all the tail latencies, because then if something starts going wrong, the highest percentiles will start reacting the quickest. And look for bottlenecks. This is everything's concurrent. So there will be bottlenecks. Sometimes they're in your application code, sometimes they're in the architecture, sometimes they're in the VM. Hopefully not that often. But the evident ones are singleton processes. It happens sometimes that people new to Elixir write a library and they want to make it look nice, so they spawn a gen server to handle all calls for completely stateless business logic. Don't do that. If you see that, tell these people, show them the way to stateless programming, stateless functional programming. Remove the singleton process if you're relying on them for any kind of heavyweight work. If there's gen server calls that you don't need because you can cheat, then cheat, because that's one less bottleneck. And counterproductive spawns. People that are fascinated by Erlang's or Elixir's parallelism will spawn everything because it's so cool to spawn, but sometimes it just doesn't make sense. Just write the code. It's usually fast enough. If in doubt, the log counter is your friend and teacher. It's a really fascinating thing to run. The other takeaway is to engage the community. I don't think I need to tell you guys. It's very important. It's a small community, smallish, but everyone has some relevant experience, and you can always learn from your colleagues. We really benefited from that. There's top VM experts at conferences, so grab them and exploit them. GitHub is good. GitHub is good because you can communicate asynchronously with the creators of the software. You can be anyone, just some guy doing some business development, and you can speak with the creators of Elixir or Phoenix Framework. It's great. And read the source. The source is very nice. It's legible. I think that's something Elixir was optimized for from the start. So it's great. Just read it, and it changes the way you look at the code, or look at the resulting application. And if you're interested in this type of work, we're hiring. That's the email, jobs@grind.com, or just talk to these guys here, all of them here. Thank you. That's it. Questions? Oh, whoa. So from 5:30 to 8 p.m. at Earl's Kitchen Plus Bar. I guess that's close by. We're having happy hour, and everyone's invited to join. Please come. It'll be fun. All
Questions? Right. Anyone? No questions, apparently. Question. Cool.
Was there any point at which you considered the ramifications of just implementing your own channels like presence feature instead of relying on Phoenix? It looks like you guys kind of kept running into, I mean, obviously you contributed a lot back to the community through submitting all that stuff, but I could see how potentially with a very specific implementation like that, there may be an argument to just kind of roll your own.
Yes, that was an argument, and that was on the table, but the calculus was we wanted something that was a common language and that we can get other people involved in, and potentially we can give back to the community, but we also get from the community. The CRDTs were a killer. We didn't want, so we spent a lot of time in the Erlang stack to remove all kinds of amnesia locking transactions. We did intense net split testing, so we were kind of PTSD'd from relying on the standard, especially in the cloud, the standard Erlang mechanism. And so the CRDTs were pretty much the killer. If we could just take the CRDTs and roll our own, that would have, but there's only so much time in the world. So yeah.
And there was another question around here. Yeah? Go ahead.
Yeah, so just to follow up to that question, so I will say the approach you're taking with channels where you use one channel process to do a bunch of internal PubSub subscriptions is actually like a recommended approach for that exact problem. So I wouldn't say that in that case that you were fighting any design considerations.
So there are some cases though, if you use the fast lane option, that you'll get stuff from the other topics, and clients will only expect stuff from their topic. So yeah, there's a bit of mismatch there.
Only the channel, the topic that you join on a channel, only that topic is fast lane to the client.
Right.
Handle info will pick up any other internal PubSub subscription. So there's no way that a client will receive an event that for a topic that it doesn't really know about. And I'll also say, so thank you very much for the pull request you sent. That's awesome. So I think we in general have a pretty flexible solution. I think the sharding was the natural way to go. It's funny, when we released Presence 1.0, I said it should work well for up to 100,000 concurrent users, but I'm going to wait for someone to find a bottleneck and then then try to make it better. So thank you for doing that.
Thank you.
But that's awesome. I think it was just similar to the original PubSub improvements, where we kind of waited until a bottleneck occurred, and then the fixes ended up not requiring a huge rewrite. It was more just, like you mentioned in the talk, find those bottlenecks and then figure out how to solve them. And usually it's pretty easy to get from A to B. And I had one other point. Oh, the task spawning. So that is our fault. That's Gary and I's fault, actually. So for the 2 million PubSub benchmark, we wanted to be able to broadcast to those 2 million users on that topic as fast as possible, because it was web scale.
Right.
So the task spawn there came out of how can we make that as fast as possible. So really, that's our fault for thinking like that's not a really valid use case for, we're not.
It was a valid use case for 2 million users.
Yeah. So I think in that case, that's our fault for, I think, like you said, we had such cheap concurrency that it worked well for this really tiny use case, but just removing it for the other 99% of use cases is better. So anyway, great talk. Thank you.
Any other questions? Nope. No one?
Right. If you're shy and you want to talk to us later, then yes, please come.
Okay, then, well, thank you.
Thank you.